This is video I29. We're continuing with section 5.5 where we're just learning about integration by substitution, and today's problems will be challenge problems. Okay, so this is day 2 of substitution. So question 1. So for each of these, I suggest that you pause the video and think. These will definitely challenge you. Okay, so let's say I have dx over e to the x plus e to the negative x. And note that you could have written 1 over this dx, but it's fine to have your differential right up top there. So go ahead and pause it and give it a try. There are multiple methods through this one. Okay, so I'm guessing most of us tried this method. So I don't know what I'm writing. I'm going to let u equal e to the x and just see what I get. So I know that if I have du dx, the derivative of e to the x is just e to the x. Solving for dx, so I can replace it, so everything is in terms of u. Okay, so I get dx equals du over e to the x. Okay, so let's see what happens now if I try substitution. So I get du over e to the x, right? And then here I have u. Here I have u to the negative first. And I still haven't written the e to the x on the bottom. I don't know what I'm writing there though. U to the negative first. And since e to the x is u, I can have du over u like that. And if I distribute on the bottom, and maybe I'll make it more clear by pulling the du out in the end, I get u squared plus 1 du. And I know we haven't done a lot of integration, but this, I'm hoping, is recognizable. The antiderivative, what we could derive to get that, is the inverse tangent of u plus big C. So that was a very tricky problem. And here's a much harder one. Secant x dx. All right, so pause if you're up for a challenge. I think this one takes a great amount of creativity on your part. And I'll start right now. Okay, so somebody had this really clever idea, and actually it was logically thought through why this would work. We don't know what we could derive to get a secant. Okay, if that's secant squared, we know the antiderivative of secant squared. If this is secant tangent, we know the antiderivative of secant tangent. We don't know that. But somebody thought, why don't I multiply this by something over itself so that the two things I just mentioned come out of this problem? And so what we're going to multiply this by is secant x plus tangent x over itself. Okay, so I still have the dx. Truly, that should be written in the end there. But if I distribute now, I get on top, I'm distributing as secant times secant, so secant squared, that's nice, plus secant tangent, which is also nice, all over secant plus tangent dx. Okay, and so now maybe pause again and try to finish this problem. And I'll start it up in a second here. And so what we see is that if I let u equal this, so I'm going to let u equal secant plus tangent. When I derive this, note that I have the chain right up top. So it was a very clever idea that somebody came up with. So I have the derivative of secant, remember, is secant tangent. The derivative of tangent is secant squared. And then I guess I should write this. I'm going to solve for dx so I can replace this. And box this up. Here's our substitution box. Did I so usually when we do substitution, we don't show so thoroughly every step. Okay, and so I'm not going to show where I'm actually doing the substitution and then later reducing. I'll reduce this and this, and I simply get 1 over u du. Okay, so this is a really tricky one for now because it's new to us. Okay, but this is a linear factor on the bottom. I don't add 1 and divide by the new. That's a natural log. Okay, and so the natural log of the absolute value of u plus big C. And then u is secant plus tangent. So that was definitely a tricky problem. Let's try another one. Okay, so this is problem 3 for the day. Go ahead and pause. Try it. Okay, so let's see what we can do. What I notice is that if I let u equal this, its derivative is 2, and that x will not go away. Okay, but here's a clever little trick. I am going to let u equal that. And I'll derive it. I'll solve for dx. But then I'll notice that this in no way helped. Because if I do my substitution at this point, sure, I'll have u to the 1/2, I'll have du over 2, but I'll have an x there. And we have to remember that everything has to be in terms of u. Well, why don't I then say, well, if u equals 2x plus 1, 2x would be u minus 1, or that x up there, I can write in terms of u. So u minus 1 over 2. So a slightly bigger substitution box. And so let's see if this helped at all. Maybe we've gotten nowhere. And so the x is, I'll put the over 2 out here. That 2 became that. And so u minus 1 times u to the 1/2 and du over 2, maybe I'll make that a 4 now. There's the 2 2's on the bottom. Okay, and then maybe this doesn't look clear, but since we can integrate term by term, I'll distribute the u to the 1/2, and I get u to the 3/2 minus u to the 1/2. Note that since I have multiple terms, I use parentheses around the integrand. Okay, and then, let's try to do this quickly. I have the 1/4. I'm going to add 1, I get 5/2, right? So u to the 5/2 times 2/5, or divide by the new. And this one, u to the 3/2 times 2/3 plus big C. I'll distribute the 1/4, and so I get 1/10, and I'll replace the u's. Okay, let's try another challenging problem. Let's do this one. Okay, so note the incredibly long integrand. This one is going to require multiple substitutions. And I always like to start on the inside of whatever kind of composed function I have. So I'm going to let u equal 3x minus 1. du dx is then 3, so dx that I have to replace is simply du over 3. Okay, this will shorten it. I have to write it again, but it will at least shorten what I'm writing. And I want to write that 1/3 out in front. Okay, next, I have to get rid of some of the sines or cosines or something here. And so, nicely, I could let u equal, or not u, because we already have u, maybe v equal sine, because its derivative is cosine, and the cosine will reduce. I could maybe let u equal cosine, because the sine will reduce, but then we'd have to worry about that one. So I'm going to say let v equal the sine. So then dv that's a v, dv du, the derivative of sine is cosine, and then solving for du now, I get dv over cosine. And in doing that, we can see that that cosine right there will go away for us, so I'll continue this now. So I have the 1/3, and then I have 1 plus v squared, the square root of 1 plus v squared times v, and then these cosines reduce, I'm not going to write that, dv. Okay, and now I see that if I were to derive this, I'd get a v somehow in there. And so I'm going to make another substitution. I don't know why I wrote that already. I'm going to write w equals 1 plus v squared. Because then I'll just have the square root of w. That's simple. dw dv, because I have to replace the dv, is 2v. Solving for dv, that's a v there, is dw over 2. A third substitution. Okay, note that I have the 2 and the 3. I'll put a 1/6 out in the front. This will become w to the 1/2. The v's, oh, I lost my v there. The v's reduce, and I just get dw. And so let's integrate. I'm going to add 1, so I get 3/2, right? So 1/6 times w to the 3/2 times 2/3 plus big C. But now we have to undo all of these substitutions. Okay, and so I get 1/9. W was this right here. So I have 1 plus v squared to the 3/2 plus big C. But v was sine. And finally, u was 3x minus 1. Not a very intuitive answer. Okay, so last thing I want to teach you in this video is I want to remind you of 2 trig identities you would have covered in earlier this year, but also in pre-calc. But I'm going to write them differently than you would have seen them. These would have been the double angle identities. Sine squared x equals 1 minus cosine 2x over 2. So cosine 2x had a number of different ways in which you could write it. Okay, one would have had a sine squared in it, and I just solved that for sine squared. And another would have had a cosine squared in it, and it's almost the same thing. And the reason I'm giving this to you right now is because if we ever end up with a sine squared or a cosine squared in an integral, we want to replace these. If we can't otherwise get rid of it, we want to replace them using the double angles. Okay, so this will be our last problem of the day. This is problem 5. So let's do a simple one. Cosine squared x dx. Okay, so immediately you think, well, can I antiderive this? Do I know what I could derive to get that? And the answer is no. And then you think, well, is there a simple substitution? If I let u equal cosine, will everything reduce? And no, it doesn't. So then I go to this, the old double angle identity. I can replace cosine squared with 1 plus cosine 2x over 2. And then if it's not very clear, I realize I can maybe pull the 1/2 out. And then I have terms. I can antiderive each of those very simply term by term. So I'll put the 1/2 out in front. The antiderivative of 1 with respect to x is just x. Now, we learned that we can use substitution, let u equal 2x here, and we would be dividing by that chain. Let's try to avoid that. That's time consuming, and we typically don't have a lot of time. So what's the antiderivative of cosine of something? It's just sine of that something. But if I were to derive sine of 2x, I would get cosine 2x times 2. I don't have a times 2. And that's why we're dividing by that chain on these. Okay, so like I said earlier, you can now do problems 29 through 40 on the review.